Partito. Benissimo. Posso dire, chi lo presenta? Roberto.
Oh, Mosco.
Va bene, allora il seminario di oggi della serie Seminari Generali dell'IAC 25 sarà fatto da Simone Creo, del Dipartimento di Scienze di Base Applicate di Ingegneria, SBAI, e ci parlerà di problemi al bordo su frattali. Forse in inglese.
Okay, so first of all, thank you very much for the introduction and for the invitation. It is a great honor to be here to make this seminar in front of you and everybody also watching from online. So today I will try to present you some results about my research, which is mainly about the study of boundary value problems on fractals. I will try to build a bridge between something more theoretical and try to explain which are the main difficulties on from the theoretical point of view in studying these boundary value problems in domains with this kind of boundary. And then I will also try to convince you on why they are important from some real-world applications which we studied, and also by showing you some numerical simulations which we conducted on some problems on fractal domains with fractal boundary, let's say. Okay. So I will first try and give you some preliminaries about fractal sets, so which are the main features and some let's say very important results on general fractal sets which we use during our research. Then I will divide my talk in two main parts. The first part I will try to focus on some scalar problems in which we study. This will be, let's say, more theoretical, and we'll present some of the results on these kind of problems. And then in the last part, I will move to some vector problems, which are more application-driven, let's say, are more driven by mathematical physics. And I will show there some simulations and some numerical results which we obtained in this problem. I just want to point out, I will try to be as less theoretical as possible, but some things about theory I should give you in order to be self-consistent. Okay, so first of all, why is it important to study boundary value problems in domain with fractal boundary? Because now there has been a lot of evidences showing that there are a lot of industrial processes and a lot of natural phenomena which occur across irregular media, which can be boundaries and interfaces. For example, there are some models of the lungs of the alveolar regions which can be modeled by fractal sets. So the boundary value problems on fractals can be also used to describe how the oxygen gets diffused around in the alveolar region. Moreover, there are also very recent results which show that there are some natural proteins which actually self-assemble themselves in fractal structures. So, and this could be a very interesting topic to attack. So, it is mandatory from a mathematical point of view to try and give a precise mathematical formulation of these kind of boundary value problems. And the fractal boundaries are useful because they are the main prototype of a domain with irregular boundary. And the study of boundary value problems in domains with the fractal boundaries model well of all those phenomena which occur in media which have a small volume and very large surfaces. Here I show you, for the sake of simplicity, two typical examples of fractal structures. From the two-dimensional case, we have the bounded domain having as boundary so-called snowflake. And sometimes we also use a kind of a three-dimensional generalization of a kind of a cylinder having as a lateral surface a fractal boundary. So these are the main two examples which I will show you during this talk, but obviously there are a lot of different more examples. So now we try to explain to you the philosophy of our group in a very few words. So as I was saying, first of all, it is important from a mathematical point of view to give a complete analysis of these problems regarding, for example, wall closeness, regularity results, and so on. In this case, the main difficulties is try to generalize a lot of results which are known in the smooth setting to the non-smooth setting. Because here, some of the results which are known in the smooth setting, we need to prove prove from scratch, because they are not known in the non-irregular setting. So this is the main difficulty of dealing with the domains with fractal boundary. Then, from the point of view of application, it would be crucial, if possible, to approximate the solution of these problems in terms of solutions of, let's say, smoother problems, so problems with smoother structures. And to understand whether it is possible to prove actually the convergence in some weak sense of the solutions of these approximating problems to the solution of the problem in domain with fractal boundary. This can be done sometimes by using an appropriate notion of convergence, which is the one of M convergence, Moscow convergence of energy forms. And this is obviously a very weak sense of convergence, which I'm going to present in a part of my talk. Oh, the other way. Opla, too much. So, let's go this way. Okay. Lastly, sometimes we also try to make a numerical approximation, as I was saying, of our problem. Our aim is to make some numerical simulation, but also to prove some optimal a priori error estimates for the numerical approximated solution, and try to see whether the numerical solution actually converges to the prefractal solution. Because obviously, when we make the numerical approximation, we never deal with a fractal, but we deal with a kind of approximation. And then we'll be more precise in a moment. The long-term goal of our group is to close the gap and to go from the solution of the numerical problem to the solution of the fractal problem, but it is still an open question, since there are a lot of technical difficulties.
So it's open at what level?
Yes. No, okay. No. Okay. Allora, we know this convergence, the convergence from the approximating solution to the fractal solution, as n goes to infinity. N is I will be more precise in a moment, but n is the order of approximation of the fractal, let's say. So, this step we know. We know this step, the convergence of the numerical solution to the prefractal solution. But if you want to make the simultaneous limits of letting both h to 0 and n to plus infinity, and to prove that the solution of this actually converges to the solution of this, then it's not possible, because there is a problem of norms. And it's not so clear how to prove exactly the simultaneous convergence, let's say, because there is a problem of functional setting. We think it could be done. But up to now, up to our knowledge, it has not been done, and it seems that there are some technical.
Probably you have to relate the H and N.
Yeah.
The speed of convergence in H has to be related to N, otherwise.
And the problem is that since the problem is that since while here we have an estimate, as I was saying, of the rate of convergence, here we don't have an estimate. We just know that. The solution converges to the solution, but we do not know the speed. So if we are trying to exploit this convergence in order to achieve an actual estimate, in order to see if there is a link between the two. But up to now, we cannot, since we have only a theoretical result which doesn't tell us anything about the rate of convergence in the N for N. So this is what we are trying to do, but it's not so obvious up to now. Okay. Thank you very much for your question. Okay, so now a few words on how actually you can construct a cone snowflake. So actually, there is obviously a more mathematical definition, but there is also, let's say, a geometric idea. Let's start with a unit triangle, a equilateral triangle having as unit side length. Then we divide each side of the triangle in equal parts. We remove the middle part and we replace it with another equilateral triangle without the base. And so in the second step, we have something like this. This is, let's say, the first iteration of the Cox snowflake. Then we iterate this procedure on every side, and we obtain this. Okay. Sometimes it goes, sometimes it doesn't.
No, but that's consistently. You see, there's some arrows.
Yeah, okay. So then you iterate this procedure and you obtain this one, and then you go on and on and on, and after an infinite amount of steps, let's say you obtain the fractal set. Okay, this is a rather geometrical construction from the point of view of, let's say, mathematical analysis.
Going back for.
Okay. From the point of view of analysis, more precisely, we can say that the Koch curve is actually the unique fixed point of this set of contractions, which acts, let's say, starting from the unit segment and then applying this set of contractions to the unit segment, having all the same ratio, which is 1/3. And then you obtain, these are the set of contractions in order to obtain this, which is the so-called Koch curve. And then the Koch snowflake is actually obtained gluing together 3 copies by adding some rotations, some translations, and so on. Okay, so from the mathematical point of view, which are the main features of fractals? So as I said, these are very irregular structures, but they have some properties which help us in our mathematical analysis. So first of all, just to say that these kind of domains belong to a more general class of domains, which are the so-called epsilon delta domains with boundary sets. I will not go into details since they are very technical, but again, they are not only fractal, but the fractal are part of this kind of domains. So from the mathematical point of view, these domains with fractal boundary enjoy some properties which are good for our analysis. First of all, by using the theory of Johnson and Wallin, they are so-called extension domains. So there is an extension operator. We can build an extension operator from omega to the whole and two-dimensional and dimensional space if needed. So there are some results which we can Johnson and Wallin actually constructed this extension operator. Then, since we are dealing with boundary value problems, it is mandatory to know how to make a trace on this kind of domain, on this kind of sets. And actually, again, by using the theory of Johnson and Wallin, here I recall here the trace theorem for the sake of completeness. We can define the trace on a domain with an irregular boundary, and the trace space is actually a Bezos space. Sometimes we will use these Bezos spaces in a particular way, since they are very complicated in general, but we will use sometimes the case in which the exponent alpha is between 0 and 1. But this is beyond the point. So, but actually, we can make the trace on a domain with a fractal boundary by using this theorem. Then this is something which I will be more precise in a moment. Actually, there is a way of defining in a very weak sense what does it mean to make a normal derivative on a domain with a fractal boundary, and also to construct an energy if needed on a domain on an irregular boundary. But I will be more precise on this in a moment. But the main thing which you need to use in order to do this is this following property, which I, let's say, briefly talked about before, is that our domains with fractal boundary actually can be approximated by a sequence of so-called prefractal domains. The sequence is denoted by omega n, is an invading sequence from the inside made by bounded and Lipschitz domains, which are typically non-convex, and such that our final domain is obtained as the infinite union of all of our domains. So this is a very important property of approximation of our domains with fractal boundary, which will help us in particular improving our convergence results in particular. Okay, so now I will try to go more into the details in some of the results. I will make a brief survey of some of the most recent results of the last, let's say, 5 years to our group. I will start firstly by presenting you this result which we obtained with Maria Rosaria Lancia and Paola Vernoli, which are both from SBI. Paola Vernoli now is retired, but she was from Mazza actually. And in this case, in this paper, we investigated the following problem, which I formally state here. So, in order to fix our ideas, we take our domain Q, which is the cylindrical domain with fractal boundary, which I showed you before. So the problem which we formally state is the following. We have a parabolic equation for the regional fractional Laplacian inside the domain, coupled with a kind of a Robin boundary condition, in which we have this object here, which is a kind of normal derivative acting on the boundary of the domain. So in order to, before going on, I need to obviously define how I can make a normal derivative on such an irregular boundary, and also to define the operator which acts inside. Here, I just, for the sake of completeness, recall the notion of regional fractional Laplacian, because obviously there are a number of different definitions of fractional Laplacian in the literature. We use the regional one, which is defined as this integral in the principal value sense, which is the one which allows us to consider, let's say, more complicated boundary conditions. And this has also been studied first in a probabilistic setting at the beginning of the 2000s, and then in the last 20 years it's been studied in a lot of papers. And this kind of operator actually usually describes an anomalous diffusion. So when you have something which deviates from standard diffusion. Okay, now focusing on the boundary condition, how is it possible to define a normal derivative, a kind of generalization of normal derivative on a domain with a fractal boundary? And this is what we did.
Is there
yes.
some correspondence with the usual Laplacian? It seems that for s equal to 1, you have not.
No, there is. You can prove some limit sense let's say you can prove that if s tends to 1, for example, you retrieve the h1 norm, let's say, by a constant. You need to put the normalizing constant.
So if s tends to 1, then this is sorry.
No.
This is the vertex, and then if you multiply by 1 minus s, then you recover the standard Laplacian.
Yeah, there is the big famous paper by Burgembresis and Mironescu of the early 2000s, I think, or late 90s. I don't remember.
This you can prove in which sense you want. So also for geometric flows, you can prove that the geometric flow with governed by the fractional norm, fractional curvature of the sense. So in each sense you want to imagine, then you arrive at the same conclusion. Whereas for instance, to theory, you convert to the identity.
Yeah.
Okay, because it's strange, because you obtain 5, 2s plus 3 is 5, and 5.
No, it's d
No,
plus
you
2s.
Yeah.
It's d plus 2s.
In this case, it's
okay.
Here is
previous
yeah,
slide,
it's there. Yeah.
In the previous slide, in the definition, you have 2.
Yeah, but there is this constant here, which now it's not. I have not the. There is the. I have the definition, but maybe.
I mean, it's d.
No, okay.
5 is not smooth. It's fact
No,
it's d plus 2s.
Yeah, here there should be n plus sp if you make also the p case.
Okay.
And n plus sp, and this proved that if you put in front a normalizing constant, then there is a convergence. But you need this normalizing constant, because otherwise you don't retrieve the convergence. Yeah.
From this definition.
No, it's not. Yeah, I understand. Yeah. Okay. So, actually, what we proved in our paper, going back to the normal derivative, is that actually we can define this object as a linear and continuous operator acting on these Bezo spaces, which is actually not the usual Bezo space, but I'm not going into details because it's very technical. But there is a linear and continuous operator on this Bezo space, which is characterized by the following green type formula. And so we call it normal derivative, fractional normal derivative, let's say, because we prove that it is defined by a green formula. So in some sense, we actually retrieve, in a very, very weak sense, what does it mean to make a normal derivative on a domain with an irregular boundary. And we prove this result by a limit argument, by using, again, the sequence of prefractal domains, which are Lipschitz, and on there we have a notion of a normal derivative, again, very weak. But by making an approximation and the limit procedure, we can actually define this object as a limit of something which acts on the prefractal.
But anyway, your normal derivative is defined almost everywhere. Because anyway, even in the approximation case, you have the area, so
because it's Lipschitz, yeah. But okay, obviously here we don't record so much, because actually here there is a lot on the fractal. It's not really, we don't retrieve something so strong, because actually. So the only thing which we retrieve is that the normal derivative is characterized by this green formula.
Yeah, but when you have the approximation, you have on the flat side, you have the usual one. On the spike, you have nothing, because
sure, because sure. And that's why we need. Since it is defined, then we can use the notion of normal derivative on domain. Let's say Lipschitz domains, polygonal domains, in order to make a limit procedure. Let's say. And we also proved that this notion is consistent with the literature, since, by going back to your question, when s tends to 1 from the left in this formula, then we actually recall that in this formula we recall the notion of normal derivative, which was defined and was the formula was proved by Maria Rosaria and Paola in 2013 for fractal domains. So this is a notion which is consistent, let's say, with the literature which already existed. Okay, so this is how to define everything on our domains with the regular boundary. So now, how to try to prove the well-posedness of the result of the problem which I formally stated before. So we need to introduce an energy form here. We put ourselves in an Hilbert setting. So we put the Hilbert space equipped with the L2, with the measure M, which is the sum of the Lebesgue measure inside the domain, and a surface measure which can be defined on the lateral surface. The domain of this energy form is defined in the obvious way. The strategy is the following. We will prove some properties of our energy form. Then to this energy form we will associate an operator which will be the generator of a family of semigroups, because the theory of semigroups is the one which we use sometimes for proving this result. So we prove some properties about the energy form, in particular this closed energy form. Then by using the theory of Kato, there exists a unique operator which is associated with this energy form by this identity, and the domain of the energy form is also of the operator is dense in L2. And lastly, in a few words, this operator is the generator of a family of semigroups, which is actually strongly continuous, analytic, contractive, and so on. And it is also ultra-contractive. So this is a lot of very theoretical properties, but it is something which we need in order to prove our well-posedness. And what we can prove actually is that the formal problem, which I stated before, actually admits a unique weak solution, in the sense that the equation inside is satisfied almost everywhere, while the condition on the lateral surface is satisfied always in a very weak sense, because it's satisfied in the dual of this Bezo space, so it's very weak. But actually we can give a meaning to the solution of this problem. And just a few words on how to reach these existing uniqueness results. First of all, we need to consider an abstract Cauchy problem involving the operator associated to our energy form. By the theory of semigroups, in particular the theory of Alessandro Nonardi, we proved that there exists actually a unique classical solution of our abstract Cauchy problem. And then by using the fractional Green formula and the properties of our energies, we are actually able to prove that the solution of our abstract Cauchy problem actually solves this problem. So we are able to prove the well-posedness of our problem. So this covers the existing uniqueness result.
Yeah. I have just a question on the boundary condition.
Yeah.
I didn't notice before. Why we have the time derivative in
Also in the boundary, yeah.
Because it's the standard parabolic problem is not.
You don't have it, yes. It's
you don't need this.
Eh?
You can prove without.
No, yeah, sure. It depends just on the. Okay, you can prove also something which is without this. Yeah, it depends on the let's say on the functional setting which you use. We use most of the times we also use this kind of boundary condition because there are some references in the literature, also something which was found before, in which it is interesting to put something let's say dynamical also on the boundary conditions from the point of view of some applications also in now I don't remember exactly, but there are some papers in which they consider the so-called dynamical boundary conditions, which they have also time derivatives also on the boundary. So,
okay. So it's not necessary.
No, it's not necessary.
It's more than.
Yeah. It's more than. It's not necessary. Okay. So now the question which remains open is how to approximate the solution. So as I was saying, okay, this is a very theoretical problem, let's say, very abstract problem. Now, what can we do in order to approximate the solution in order of something more, let's say, touchable? So we need to introduce a sequence of approximating problems on our domains Qn, which are the prefractal domains which I mentioned before. So in order to do so, since our domains actually vary according to n, then we introduce a sequence of energy forms which varies according to n, and also we introduce not only an Hilbert space, but a sequence of Hilbert spaces which vary according to n. And the main feature of this energy problem is in particular this factor delta n here, which is in front of the boundary integral. Okay, as to the existence and uniqueness, there is nothing to be seen because the standard techniques are actually easier, since here we are dealing with Lipschitz domains. Here I just present the existence and uniqueness result, just to point out that there is this factor delta n, which is up to now a positive factor, fixed, appearing also in front of this boundary condition, which will play a crucial role in our convergence result. And how we can prove the convergence of the prefractal solutions to the solution on the fractal domain, we need, as I was saying at the beginning, the notion of Moscow convergence of form, which was introduced by Umberto Mosco in the 1969, then was generalized to the case of varying Hilbert spaces, which is our case because we have a sequence of Hilbert spaces by Guai and Shioya in 2003, and then by Tolle to the nonlinear case. Here, for the sake of completeness, I record the definition, which is, for those who know, kind of similar to the gamma convergence. Actually, it is a bit more general, the gamma convergence, but it is kind of similar because we have a limit condition and a subcondition to be proved. And what we are able to prove in our case is that with this particular choice of the factor delta n, which is linked to the Hausdorff dimension of the Koch snowflake, then the sequence of Hilbert spaces converges to the limit Hilbert space, and also the sequence of forms Moscow convergence to the limit energy function, energy form. So I just want to point out that this constant as n goes to infinity goes to 0. And it is in front of the boundary integral, since in some sense it is balancing the fact that the measure of the prefractal goes to infinity as n goes to plus infinity. So we have a kind, something goes to 0, something goes to infinity, it balances, and then it produces a finite limit, let's say, at in the limit. And so this is a kind of, it is an intuition. It's not something very rigorous, but it's an intuition which is the role of this constant. And then here is the main convergence result, because we prove, actually in a very weak sense, obviously in a very weak topology, that the solution of the prefractal problems converges to the solution of the fractal problem, firstly for every fixed time, then also with time varying, and then also we can prove in a very weak sense the convergence of time derivatives of operators and of normal derivatives. So we have a lot of results, and these are all consequences which can be proved by the Moscow convergence of the energy. So this Moscow convergence of energy is a very powerful tool which allows us to prove a lot of different conditions. Okay, now we can obviously try and play the game of going to the nonlinear case, and this is actually contained in another paper. What happens if we consider a slightly different boundary condition? So we're not talking no more about the Robin boundary condition, but we talk about Wenzel boundary condition. And so this is a result which is in this paper with Maria Rosaria. So the problem is, let's say, a nonlinear generalization of the previous one, but with an additional term on the boundary, which is another non-local term, which is a kind of fractional Laplacian localized on the boundary. So in this sense, we call it a Wenzel problem, because Wenzel problems are quite strange, let's say, because they are characterized by the presence on the boundary of an operator which has the same order of the operator acting inside the domain. So, for example, if we have the equation, for example, we have the Laplacian inside and the second order operator acting also on the boundary. In this case, we have two kinds of fractional operators in some weak sense. The theory is the following. These are the steps. As before, we need to introduce some properties of our energy, of a suitable energy function, which needs to be defined. We consider firstly an abstract Cauchy problem involving the subdifferential of our operator. This is actually very more complicated than the linear case. But by using the theory of nonlinear semigroups, in particular the theory of Bretis and Barbour, we prove that the abstract Cauchy problem meets a unique strong solution. And then we prove that actually the solution of this abstract Cauchy problem converges to solves also the problem which I formally stated before. But this can be done, but I'm not going into too many details because it's very technical. This is the final existence uniqueness result, in which, again, the boundary condition also in a very weak sense because it works in the dual of the Besel space. Here, we are in the two-dimensional case, but it can be done also in the three-dimensional case and even in a more generality. But the focus of this paper actually was something different because it was on proving this main result, which is the ultracontractivity of the nonlinear semigroup, which is a kind of regularizing effect of the semigroup, because in some sense, this estimate tells you that the semigroup, nonlinear semigroup, maps LQ in an infinity, in some sense. So it has a regularizing effect. This is something which was, again, known in the smooth case, and we generalized by using, for example, a logarithmic fractional Sobolev inequality to the case of irregular domains. In particular, all these exponents here depend in particular on D, which is the absolute dimension of the cosmology. So the irregularity on the boundary actually plays a crucial role in this estimate and on the speed of propagation, let's say, of this on this estimate. And this is again a very important result which was proved for the first time in our paper. Okay, now I'll try to give you something, let's say, more. This is the branch towards something, let's say, more applied, because starting topic which we are starting now in collaboration also with Gianluca Mola and Silvio Romanelli is the study of inverse problems in irregular domains. In particular, how to approximate the solution of inverse problems in irregular domains in the spirit which I already explained you. So this paper is actually not yet published, but it's accepted. I hope it gets published soon. Okay, so first of all, what is an inverse problem? Which is the spirit of inverse problems? Okay, well, everything which we've done up to now can be called the direct problems, because we have, what do I mean by direct? We are given some data, initial data, source data, and so on, and we want to find a solution U. What is an inverse problem? The spirit of inverse problem is the following. If you give a datum, for example, an initial datum, in some sense, from a physical point of view, you have to measure it. But to measure something, it can be very expensive from a point of view, also very difficult, and also impossible in principle. So in inverse problems, actually, we aim to give less data and to retrieve it after. So this is a clear example which maybe can be more useful. Okay, let's say that we want to know the trajectory of a body given its at some time t. Then by Newton law, we know that there is the second Newton law, so we have this ordinary differential equation given the initial position and the initial velocity. The key role now is played by the mass in front of the velocity. It can be thought as a datum or as an unknown. So, for example, if m is we want to understand the trajectory of an apple, then it is easy to measure the mass of an apple. So, in this case, we can think of the m as a datum. And so, in this case, we have a direct problem. We are given the force, the initial data, the mass, and we can find the position. What happens if we want to know the trajectory of a satellite? So to know precisely the mass of a satellite, it can be very difficult. For example, it can be very expensive to know how much exactly, which is exactly the mass of a satellite. So in this case, we can think of m as an unknown on this problem. And now this becomes an inverse problem. In the inverse problem, we want to find both the trajectory and the mass. So which are the main differences from the direct problem is that this problem now is nonlinear, because we have the product of two unknowns. And it is in general not well posed, because we lack some information in order to retrieve a unique solution. So in order to retrieve the well posedness, we need to add some informations, which are in the literature sometimes called over-determining conditions. So we need to add some information. Obviously, in the literature, there is a number of different conditions which can be added. It depends on the nature of the thing which you want to identify. Here I present you two examples which you can think of, but there is a lot of different measurements which you can give. Okay, now this is some idea on how to investigate an inverse problem. Now, okay, I will make an abstract setting, which is more or less the same which I used before. We use energies with some hypothesis, in particular, it is a Dirichlet form on this domain, which is L2 of omega. Then our strategy is the following, is the same as before. We introduce an operator by a theory of Kato, which is the generator of a family of semigroups, and so in some sense we are able to prove that the direct problem admits a unique solution. Now we focus on the inverse problem. So the inverse problem states we want to find the solution U and this constant alpha here, which is kind of the conductivity, let's say, of this problem, which satisfy this abstract Cauchy problem with this additional measurement. So we suppose to know the L2 norm in this case of the solution at some time t, capital T, which we fix, and we suppose to know that this quantity is equal to some rho, which is given for us. So this is the overdetermined condition which we had in our problem. So the whole process of this problem is actually known in the literature in this paper by Gianluca Mola of 2018. And this actually is done by hands because he exploits the explicit writing of the solution of the abstract Cauchy problem in terms of the semigroup, which is generated. Then they define these functions, which is a function of alpha, and then they make some computations and they prove that actually the solution is unique. And there is also continuous dependence on the initial datum and on rho. Our aim in our paper was to prove the convergence. So we want to know how to approximate the solution in the space which I was saying before. So we need to introduce again a sequence of energy forms such that in particular it Moscow converges to the final energy form which we have. These are two of the main consequences of the Moscow convergence, which in particular imply the convergence of the semigroups and also the convergence of resolvents. And this is why I was telling you that Moscow convergence actually is a very strong tool because it has a lot of consequences very important for us. So here I present, for the sake of completeness, the inverse problem in the approximating sense, let's say, which is again the structure is the same as before. And what we are able to prove is this very abstract result, actually, because in this, I should say that in this result, the fact that omega is an irregular boundary doesn't enter too much. So this can be generalized also to a much more abstract setting. And we have that under suitable hypothesis. Then we have the convergence of the solutions and also of the couple of the solution, which is now given by the conductivities and the solution of U. And so we can actually prove that the solution actually it can be approximated in terms of something smoother, let's say. The main tools of this problem are actually, again, it can be done by hands, let's not easily, but can be done by hands by using a contraction argument, and actually this abstract result, which is contained in this paper by Barbinek, Daller, and Franco, which actually allows us to prove the uniform convergence of some sequence of inverse functions, which is, again, very abstract and very useful in our results. So just to show you an example, this can be used in order to prove the solution of the convergence of the solution of homogeneous heat equations for the Laplace operator in the domains with fractal boundary. Here, just to recall the setting, we introduce the usual Dirichlet energies. It's actually easy to prove that this sequence of energies actually converges to the limit fractal 1. We introduce, I will skip this because this is, again, I will go to the last slide. These are the abstract problems. We prove that actually these problems admit weak solutions in which we have, again, homogeneous Dirichlet boundary condition for simplicity, because this setting allows us to consider this case. This is for the fractal case, this is for the prefractal case. And then we are able to prove, again, in this case, that we can approximate the solution of the heat equation on a domain with fractal boundary with the Dirichlet boundary homogeneous Dirichlet boundary conditions in terms of the solutions of corresponding problems in the domain with prefractal boundaries. Just want to mention that this is a preliminary step because this was again not known in the literature. It's the first result of this kind. Our aim is obviously to consider again more complicated boundary conditions than homogeneous Dirichlet. We are trying to work on it. There is also another application, but I will skip it in order to go directly to this one, which I will try to conclude with this. And as there are two domains now, I saw. Okay, as I promised, I will try now in this last part to talk about vector boundary value problems, which is a very rather new topic on the last 5 years in our group, in which our philosophy was to start from very simple examples of problems of mathematical physics, Maxwell equations and Stokes equations, then solve them in domains with fractal boundaries, and then try also to approximate the solutions in terms of some Fields model, and then also to perform some simulations. So to understand how fractal structures react when they are, let's say, when there is a fluid passing through, let's say, a tube, or we have a magnetic field inside the domain with fractal boundary. So I will start, first of all, with this magnetostatic problem. We start from the Maxwell equations, we make a lot of assumptions, and we simplify the model, and we retrieve this so-called stationary magnetostatic problem. We consider for physical relevance the three-dimensional case of the cylinder. So here Q is again the cylinder with lateral surface fractal. We have divergence of Q equal to 0 and tangential component equal to 0. Okay, so the first question is how to define this boundary conditional domain with the fractal boundary. And this again is done by proving a Stokes formula this time, not a Green formula, but now a Stokes formula. Again, the proof of this theorem is made by limit argument by using the approximating structure which we have underlying of the prefractal domains. Now, in order to prove, first of all, the well-posedness, since we are interested also in the well-posedness, we introduce a suitable linear form, a suitable functional, and let's say by Lax-Milgram, basically we can prove that actually our problem admits a unique solution of the magnetostatic problem, which satisfies also this estimate. And the main tool for proving this result, in particular the coercivity of this energy form, is a Friedrichs type inequality, which we proved again for the first time in a domain with an irregular boundary, because it is something which allows us to prove the coercivity. Now, as I was saying, for the point of view of applications, we are actually wanting to investigate something numerical. Obviously, from the numerical point of view, it's better to see something in 2D. So in this case, I will see something in 2D. We make an axial symmetric hypothesis. So we reduce the three-dimensional problem to a two-dimensional one. We consider this is the problem in the fractal domain. This is in the prefractal domain. And what we prove is that when the length of the boundary increases, omega 0 for reference is the unit circle. When the length of the boundary increases, actually also the magnetic field increases. So there is this relation of how the magnetic field behaves when we consider an increasing number of iterations of approximation of the prefractal. Here there are a couple of pictures. So we put a Gaussian source term inside of the domain, and after some time you can see that it is, let's say, diffused around the domain and is concentrated around these points. This is rather strange, was rather strange for us, but there is one of our co-authors, which was Alexander Teplayev from the University of Connecticut, told us that is actually there are some experiments by the group of Ackermans which actually are consistent with this. So this is the third approximation of the Gauss snowflake, and this is also the fourth one, in which you see that there is again more concentration of the magnetic field around these corners. Now, lastly, about the Stokes problem. Here we stay with the prefractal domain. We consider a parabolic incompressible sort problem. So we have the equation, which is also stated in this way. We couple it with homogeneous Dirichlet boundary condition with initial data. So again, this is the problem which we studied in the prefractal setting. We are able to prove that there is a unique weak solution by using obviously some projections and so on in order to prove that the solution is unique. And to this weak solution, we can associate a unique pressure which has zero mean value, obviously, in order to retrieve uniqueness. But since now in this paper, which was, I should say, in collaboration with Massimo Cefalo and Mirko Gallo, which are two engineers, which helped us with the physical insight to understand this problem. In this paper, we are mostly interested in showing some numerical results. So improving the optimal a priori error estimate for the numerical approximation, and also to show some numerical simulations. And in order to achieve the optimal a priori error estimate for our numerical approximation, we need an intermediate result, which was this. And this result tells us that the weak solution of our Stokes problem actually has something a little more regularity, because the solution belongs to this space H2 of gamma, and the pressure belongs to H1 of gamma, where these two are weighted Sobolev spaces. So obviously, since our domain is non-convex, obviously there is no hope of retrieving H2 regularity for the solution, for example. But for trying to obtain the optimal rate of convergence, we cannot stay just with weak solutions. We need something more. And so this weighted Sobolev regularity actually helps us in retrieving the optimal a priori error estimate. And I will tell you why in this slide. So this is a picture of how we constructed the mesh of our two-dimensional domain. Because the main point is that when considering non-convex domains, you have to in particular domains with a lot of sides, you need to construct in a precise way the triangulation of our domain. In particular, it needs to be obviously more refined near the corners, and the sizes of these triangles cannot be arbitrary. They have to be tailored, and here is the link with the regularity results in weighted Sobolev spaces, because this triangulation is constructed by complying with the so-called Grisvar conditions. And these Grisvar conditions are contained in the famous book by Grisvar in 1985, if I remember well. In this book, there is written how to construct the triangulation and the size of this triangle related with the weight exponent in the previous slide. So, in order to construct the mesh, we need to know this weighted regularity. And after we construct this mesh, we retrieve the optimal rate of convergence of the solution, of the numerical solution to the prefractal one. And we actually achieve the same rate of convergence which we would have obtained if the domain were convex of the solution were H2. So we obtained the optimal rate of convergence by using this particular mesh which we created. This mesh was actually constructed by Massimo Cefalo and Maria Rosa Lancia in 2014 in the two-dimensional case. Here we extended to the third dimension by exploiting the cylindrical structure.
But the weight of the space depends on the properties of the boundary. How do you know?
In which sense?
So to construct the mesh, you need the regularity of the weight of the space, but to determine the weight of the space.
No, the weight obviously is the distance from the. I should have said it. Yeah. Okay. Usually the weight is the distance from the boundary.
Okay.
Sometimes there are some results in which they consider not only not the whole boundary, but the so-called reentrant corners, so the corners which have an amplitude greater than pi. But they can be switched around, let's say. But the most usual one, I think, no, here we use the distance from the boundary. So that is the weight. And there is a result by there is the Russian school, let's say, with Kondratyev, which allows you to prove regulating weighted Sobolev spaces. So, and then there are a lot of information there. Yeah, but the weight is not. It is not the general weight. It is the distance from the boundary in this case. Okay, and lastly, this is maybe the most interesting application from the result from the point of view application. When we spoke with Mirko Gallo, again, who is an engineer, he told us he had this idea. Okay, if you have a tube with a lot of edges, with a lot of edges, if you make a fluid pass through this tube, in his idea, the wall shear stress, the average wall shear stress of the fluid should go down if you increase the number of angles, let's say. And he told us there is a way of proving maybe mathematically in this way. And they try. Me and Maria Rosaria, we said, okay, maybe we should try. Obviously, we define the average wall shear stress in a weak sense, where Kn here is the boundary, let's say, of the polygonal curve. And what we actually prove is that under some technical hypothesis, then the average wall shear stress satisfies this estimate. And in particular, if n goes to infinity, this tends to 0. So in some sense, in principle, if one can construct a fractal tube, so a tube with a fractal lateral surface, in principle, the stress should be 0. Let's say, if one could construct something like this. So this is a kind of rigorous estimate which we proved. And this is the numerical evidence, let's say, which we are trying to give. And here we consider up to the 7th iteration of the prefractal, and we showed that the average wall shear stress is actually going down, and this is the exponential decay of our average wall shear stress. Obviously, one could say that 7 iterations maybe is not so much, but unluckily we were working with usual laptops, with normal laptops, so we cannot go higher, so much higher in the order of iteration, because again, we are working with 3D, and constructing a 3D mesh is much more expensive than construction in 2D, and also in 2D we can now go up to 9, I think, in 2D. So hopefully we can try, but we are confident this is true. Yeah, also because we prove it mathematically, but we can also try to make some more simulations if we have, let's say, more powerful machines. Okay, here just to conclude with some perspectives. So one could have noticed that when I was talking about the problem involving the two fractal operators, one inside and one on the boundary, I never spoke about the convergence, the asymptotics. And this is due to the fact that up to some months ago, we were not able to prove most convergence of functions having a non-local term acting on the boundary. Actually, with Michael Inz from the University of Bielefeld, now we were able to prove a first preliminary result tailored to the 2 dimensions and tailored to a particular non-local term. Now we are trying to work to a generalization of this problem, which is very technical, but it could be very interesting. This has also an application in numerical analysis, since we are working with 2 colleagues of numerical analysis, Ludwig Klinteberg in Sweden and Chiara Sorgentone from SBAI, in which we are trying to study the convergence of the solution of Laplace equations with non-homogeneous Dirichlet boundary conditions by using integral formulations on the boundary. And these results actually relies on these previous results which we proved, but this is again a work in progress, since it is very technical. And as to inverse problems, with the same group as before, with the addition of Andrea Mola, we are trying to generalize the problem which I showed before to the case of fractional time derivatives of Caputo type. So we replace the usual time derivative with a fractional one. We also add not only one constant and one operators, but n constants and n operators with some compatibility conditions. The first goal is to identify the solution and all the conductivities. The second goal could be to identify also the exponent of the time fractional derivative, but in this case, the additional condition is not clear what will be, because one can write explicitly the solution of this problem, but in a much more abstract way when compared to the case when we have alpha equal to 1, let's say, unusual time derivative. So this is we will be very happy with the first step, and then if we try to identify even the alpha, we can be even happier, let's say. So this is everything. I hope that it wasn't too heavy for you, and thank you all for your attention.
I have some questions. Just about visualization. First of all, the simplest one. What about since you are interested in magnetism, electromagnetism, and so on? Why did you consider just the first derivative of the wave equation or something like that?
We are working on it because up to
once you have the semigroup in principle, you can do wave equation.
No, yeah, sure. There were some let's say how to say, some doubts, let's say, when because when we were talking with Umberto Mosco some years ago, he had some restraints on what does it mean for a wave to go through a fractal. So he doesn't have the physical insight of how to understand this phenomenon. Now, in principle, we actually
linear acoustic.
Yeah. Actually, in principle, we could do it because, as you said, since we have semigroups, then obviously we will move into second.
Even Maxwell equation.
Yeah. So in principle, we are actually moving towards this direction because we are, let's say, users of semigroups. So we are now we use it a lot of times, so we know a lot of things. So we are trying to see something about the wave equation. It's surely something which is now starting. So I didn't mention it because again we are starting now. So maybe I'm not so clear where to go, but there is something which we are seeing. We are seeing up to now. Yeah.
Okay. And for the 3D application, you just considered some cylinder. But what about, I don't know, a Menger sponge, some other fractals which are intrinsically really 3D, because the cylinder is not 3D.
No, sure. It's an extrusion. Yeah, no, I see. Okay, the problem is that we use Koch-type fractals, since again we know how to construct, let's say, energies, because to construct, for example, energy here is not the case. But maybe with this, if you consider let's say homogeneous Dirichlet conditions, for example, maybe we can consider something. So for some point of view, for my understanding, is also obviously easier, let's say, to make a numerical simulation with because it's easier to construct something like a Koch snowflake to put to give to the machine to compute. So we can try, I think, to consider something something trickier, but up to now I'm not sure how to handle it, for example, from the point of view of numerics, for example. So, and again, since we are
just for the theoretical point of view, you have a Sierpinski triangle. You generalize to 3D. You have Menger sponge, which is a sort of Sierpinski, but in 3D. It's a classical construction. So you have a simple algorithm to construct the fractal. I think that you
can be extrapolated. Yeah, maybe so. Yeah. I am not.
Most of the fractals are approximated by simple iteration.
No, I must say that I was driven through to numerics, let's say, because my thing is not numerics. But with Maria Rosaria during my PhD, she told me, okay, we need to do some numerics because our PhD is applied, surely. So we need to do some numerics. So I have not the feeling on how to construct, but I think it can be done. From my point of view, again, thinking about the theoretical side, Sierpinski for me it's okay, but since you how to know what is inside with outside, because you have a lot of
holes.
So it's for me it's a bit strange, but you can do it always. But there is a number of papers also by Umberto, by Maria Costina Vivaldi, Raffaella Capitanelli, in which they work on Sierpinski type domains. I always saw to 2D, because I think that 2D is simpler, obviously. To 3D, we can try, and from the numerical point of view, the trickiest thing I think it should be to construct the mesh. Because again, with the idea, if you want to have optimal error estimate, as I was saying, the mesh should be constructed very precisely. So for the Sierpinski can be done. For the three-dimensional case, again, we use deeply the fact that it is an extrusion. So we basically took the two-dimensional mesh and we multiply with the 1001, and so we had the pentahedral object. So with something which is not cylindrical, I'm not so familiar how to handle, let's say. But maybe it can be done, yeah.
Yeah, triangulation in 3D is not.
Yeah.
Yeah. Okay. And okay, one suggestion for the possible problem is have you considered membranes? Because there is a lot of problems where you have, since you consider the Robin condition, if you have two domains separated by fractal membranes.
Yeah, sure.
But membranes in reality are fractals.
Yeah, sure.
And we approximate usually the surface, flat surface, is not a reality. So as a filter, it could be interesting to make an extension, putting some, for instance, some jump condition on the boundary.
Sure. No, actually, if I may, there is actually a lot of papers before I arrived in the group, because there is a number of papers in the from 2000 to 2010, let's say, by Maria Rosaria, Maria Cristina Vivaldi, Paola Vernon, in which they consider actually transmission problems. So they put themselves, again, since maybe they were more interested in something theoretical, two-dimensional case, so we have a rectangle divided in two parts by a fractal surface. And then they put it equation in the two parts of the domain, and they put a transmission condition on the interface. And that is where sometimes they consider a Wenzel condition, so in which they introduce a very weak Laplacian on the Koch curve, let's say, again defined in limit sense by Lagrangian measures, so in a very, very, very weak sense. And they proved that there were poses of the problem. They also make some numerical simulations on this problem. They proved that if you put, again in the prefractal sense, so the interface is not fractal, but is a polygonal interface. They proved that if they put the source in one of the two parts of one of the two subdomains, then the heat will, the more you increase the number of iterations of the prefractal, the more heat was caught by this interface and deployed outside of the domain, and something was trapped inside of this interface, because Wenzel boundary conditions are highly conductive boundary conditions, let's say, from the point of view of also physics. Sometimes they are called in this way. So there is a number of papers on transmission problems. So because actually they started from this and then we moved to boundary value problems. We have also a kind of more theoretical results in which we have a square with inside the Koch snowflake, and we considered fractional Laplacians of different order, one inside and one outside, and we have a Robin type boundary condition with the jump of the normal derivative defined in a very weak sense. So it can be done. There is a number of works in the literature also about this.
Okay, very much.
You're welcome. Thank you.
Okay. So.
Thank you again.
Thank you.